So let's talk about Ohm's law for a minute. Um, Ohm's law is sort of the basic relationship between voltage, current, and resistance. And what George Simon Ohm figured out, and he was a German guy and was really sort of the first to demonstrate this property. What he noticed was that the current is inversely proportional to the resistance. That is to say, there's a property of lots of materials that resists charge flowing through them, right? And you can think of that a lot of different ways, but the diameter of a pipe affects how much water it can take through it. And you can kind of think of that this way. It's not the best, but there's lots of ways to have resistance to charge flow. And so the current varies inversely with the resistance. Low resistance, high current. High resistance, low current. And the proportionality constant was the voltage. And so he found that the higher the voltage you put in, that increased the current. The higher the resistance, that decreased the current. If you reduce the voltage, you reduce the current. If you increase the resistance, you decrease the current, and so on. And so this is called Ohm's law. And some materials don't work this way. So most laws are like universal, but not this one. This only applies to materials that kind of behave this way. And so certain materials are called non-ohmic, and a light bulb is that way. We did it in lab. The more current you put through a light bulb, the hotter it gets, the higher its resistance gets, and so its resistance varies. This sort of assumes the resistance stays constant regardless of what the current is. And so we can just do an example or two. So we can ask the question, what's the effective resistance of a car's starter motor if you get 60 amps through it when 12 volts is applied to it? And so if we start with Ohm's law, and so the resistance is the voltage divided by the current, in this case 12 volts divided by 60 amps, or 0.2, what we call ohms. If you remember, a volt is a joule per coulomb, and an amp is a coulomb per second, right? And so volts over amps is joules per coulomb over coulombs per second, which is joules seconds per coulomb squared, and we call that an ohm. It's a unit of resistance, and it's, we could break these down, right? A joule is a kilogram meter squared per second squared, and so this would be a really complicated unit if we wrote it down in terms of its basic units. But we just know that if we use volts and amps for voltage and current, the resistance comes out in ohms, and we can keep track of it that way. So here's another example of Ohm's law, and this has to do with humans and how to not get electrocuted. When dry, the resistance across the human body is about 500 kiloohms, or 500,000 ohms. As to say, it varies greatly from person to person. Some people have kind of moist hands. You've seen the ads for dry hands. And some people are drier. But anyway, on average, the resistance of a human who's dry is about 500,000 ohms, When wet, maybe a kiloohm, and also that depends on how wet you are and what you're wet with and all kinds of things. It turns out that the thing that makes you safer or in danger isn't the voltage that's applied to you, or it's only indirectly the voltage. What really matters is how much current goes through your body. You can touch a doorknob spark and get 10,000 volts, but as we saw earlier, a doorknob spark might be just a microamp or something like that, a very tiny current. And so there's not much danger for those things, or even a larger current for an instant is often not too bad. But a 5 milliamp current is the maximum safe a human can take. Usually 10 milliamps will kill you. So the question is, what's the maximum safe voltage you can get when you're wet, right? And so if we write down Ohm's law, it's I equals V over R. So then we can write it this way. We can say V equals I times R, right? And if the maximum safe current is 5 times 10 to the minus 3 amps, right? And the resistance when you're wet is 10 to the third ohms, right? Then that's 5 volts. Amps times ohms gives me volts. 5 times 10 to the minus 3 times 10 to the third is 5. And so this is why you have to be very careful playing with electronics in the bathtub and things like that, because when you're wet, even a small voltage is very dangerous. You want to be very careful messing with your car battery, which is 12 volts in the pouring rain. Usually those things are okay because there's a hood over them, and so most of you will be dry, but it's good to be extra careful when you're playing with electrical equipment, especially if you're wet. So we're going to talk just a little bit about resistance and what it is actually, and this property called resistivity. And so if we have a resistor in a circuit, it could be a light bulb or a calculator, anything that sort of makes charges do things. There are resistors in circuits and components that are just specifically called resistors, but anything in a circuit causes some kind of resistance usually, and so it turns out the electrical resistance of an object depends on the length of the object. So if you think of this in the sort of the hydrodynamic sense, in waters and pipes, the how far the electrical charges have to move through this object increases its resistance. The more work the electrons have to do to get through, the longer the object is, the greater its resistance is. Similarly, the resistance varies inversely with the area that the electrons get to move through. If they've got a really narrow area to go through, if the wire's really, really thin, it's got greater resistance. If there's lots of room, it's got a lower resistance. And so the resistance varies inversely with the area. And finally, it depends on some intrinsic properties called the resistivity of the material. Every material, depending on its chemistry, has what's called a resistivity, just like it has a heat capacity and a density and stuff like that. It's just a property that causes electrons to be slowed down through it that depends on its chemistry. And it turns out this is the formula. The resistance is equal to the resistivity times the length divided by the area. The resistivity is just a property, and actually resistivity depends on temperature, and we'll talk about that a little bit. The hotter something is, the higher its resistivity. But anyway, the longer it is, the greater its resistance, and the smaller the area, greater resistance, larger area, smaller resistance. So that's how the resistance of a material of an object is calculated. So we can ask the question, what's the resistance of a 20 meter copper wire that is 12 gauge? 12 gauge means its radius is 1.027 times 10 to the minus 3 cubic meters. And so if you remember from the last section, the resistance is rho L over A. And so they gave us L, which is 20 meters, that's my L. And the area is just pi r squared, right? And so we need to look up the resistivity, and the resistivity for copper, you can look it up in a table in your book if you want, or you can Google it on the internet, is 1.7 times 10 to the minus 8th ohm meters. That's the resistivity. And you can kind of see that when you multiply it by a length and divide it by an area, you've got to get ohms for resistance, and that kind of works. And so that says that the resistance for this wire is 1.7 times 10 to the minus 8th ohm meters times 20 meters divided by, and so I've got to calculate the area here. It's pi times r squared, which is 1.027 times 10 to the minus 3 meters squared. I get about 0.1 ohms. This would be a typical house wire, you know, and so you don't want your wires in your house to have much resistance. And so this is a 20-meter wire, so it's running through your house from the circuit breaker box in your garage. It runs 20 meters to your kitchen or to your bedroom or something like that. And it's got a very low resistance on it, because you want the resistance to be in the materials you're running, not in the wires. And so we can ask another question. Well, we can talk about the temperature dependence. So we write it this way. Rho is just the resistivity of a material at some temperature. Rho naught is the resistivity at 20 degrees C, room temperature, right? Delta T is the temperature difference from room temperature. So, you know, if this is in a computer, inside your computer, it might be 100 degrees Celsius or something like that. And so this would be room temperature, and so delta T would be 80 degrees Celsius, right? And then alpha, I'm going to have to write this at the top. And so I can ask this question. I can say, so we ask the question, what is the temperature coefficient of resistivity, alpha, for a resistor that has 20% more resistance at 100 degrees C than at 20 degrees C? And so if you look at this resistor, so the resistor is equal to, the resistance is rho L over A, right? And so we can say at 20 degrees C, we can say, look, the resistance at 20 degrees C, we'll just call it R naught, is equal to rho naught L over A, right? And then we'll say R1, which is at 100 degrees C, That's equal to rho L over A. Again, the length and the area are the same because it's the same piece of wire. What's different is this guy, right? And so we're saying, look, R1 is equal to, is 20% greater than R0. And you should pause this and ask you, what's the relationship between R1 and R0 if R1 is 20% greater than R0? And the answer is, it's 1.2 times R0, right? And so that means rho L over A is 1.2 times rho 0 L over A. That's what that means. R is 20% greater. It's equal to 1 plus 0.2 times R0. It's equal to R0 plus 0.2 times R0. It's 20% greater. All right, I've beaten a dead horse. The L and the A cancel here, right? And this says rho is equal to 1.2 rho naught. But we just said that rho is equal to rho naught times 1 plus alpha delta t. And that's equal to 1.2 times rho naught. Right? The resistivity is equal to the resistivity at 20 degrees C times 1 plus alpha delta T. And that's, we've already decided, is 20% greater, and so it's 1.2 times this. So if I go back up to the top here, right, I'll just write the whole thing out. I say rho naught times 1 plus alpha delta T is equal to 1.2 times rho naught. Well, if I just look at that part of the equation, I can cancel rho naught, and I can say 1 plus alpha delta T is equal to 1.2. Alpha delta T is equal to 0.2. I subtract 1 from both sides. Alpha is equal to 0.2 over 80 degrees C. The temperature coefficient of resistivity is 0.0025 per degree.